Hello, welcome to another video. As promised, this is the second video on the basic concept of matrices. So today I'm going to show you how to multiply two matrices and tell you when you cannot multiply two matrices and tell you how you can multiply two or three or four more matrices, whatever you get as an exercise. You just need to know some characteristics. So I already prepared some examples. I'm going to make up one at the end here. I have A, but I don't have F, but I'm going to show you what F could be. Let's get into the video. Remember that you must know the dimensions of all matrices you're working with. And it's easy, you just want to know how many rows and how many columns. So we know this is a 2 by 2 matrix because there are 2 rows and 2 columns. This is a 2 by 1 matrix. That's B. C is a 3 by 3 matrix. D is a 1 by 3 matrix. We know that E is a 2 by 3 matrix. Okay, that's it. So, what is it we can do? Let's start with the very first exercise here. We want to calculate or we want to compute AE, that is A times E. So we'll be multiplying this matrix by this matrix. The first question you want to always ask is, what are the dimensions of what I am multiplying? So the first one is to calculate or compute the product of A and E. So I am multiplying a 2 by 2 matrix by a 2 by 3 matrix. It is a 2 by 2. You're multiplying it by a 2 by 3 matrix. And remember, what you always look for before carrying out any multiplication is whether the inside dimensions are the same. If the inside dimensions are the same, you can do the multiplication. So I know right off the bat that I can multiply and that the answer I'm going to get will have the dimensions of the outside dimensions. So I know that this is going to give me a matrix that is 2 by 3. So I'm going to get a 2 by 3 matrix. Is there a 2 by 3 matrix here? So my answer is going to look like this. So we have 1, 1, 2, 1. We're multiplying it by E, which is 1, 0, 0, 0, 1, 1. By the way, I chose very small numbers and I put many zeros to make our lives easy. So how do you do this calculation? So this is what you do, and this is why it's important for the inside dimensions to be the same. You see, because I have 1, 1, there are 2 columns here, so it means I have 2 numbers in the first row that I need to go multiply the 2 different rows in the second one. So I'm going to actually write out what I've done. So this is what you get. You're going to get this multiplies this, the first multiplies the first, the second multiplies the second. You do that for all of them. The first multiplies the first, the second multiplies the second. You take the row and multiply the column. You multiply rows by columns. That's why we must have the same inside dimensions. Remember, this is row times column, row times column. So the column multiplies the rows. The column and the rows must be the same. Okay, so if I take this, I multiply this. Okay, so what I'm going to have is 1 times 1, 1 times 1. Then I'm going to add the second multiplication, 1 times 0. That's what you do for the first entry in your matrix. Okay, we're done with this multiplying this. Now, we could treat it this way. If we want to go down here, we can go down here and say we do the same multiplication. 2 times 1, we get 2 times 1, and then we have 1 times 0. Okay, it's going to be plus 1 times 0. So now this is the result of multiplying this matrix by the very first column. So you can imagine in your mind that you've split this matrix into 3 different columns and you're multiplying this by the first column as if you're doing this multiplication, AB. where your 2, 1 is now just 1, 0. And then you get an answer. Then you get another answer. Then you get another answer, and you're done. So let's go to the next part. Now we're going to move on and go to the middle column where 1 multiplies 0. We're going to have 1 times 0. I'm not going to do this as I continue. I just want to show you the breakdown. 1 times 0 plus 1 times 1. And then we do the same thing. 2 times 0 plus 1 times 1. 2 times 0 plus 1 times 1. And then we go to the third one. 1 times 0 plus 1 times 1. 1 times 0 plus 1 times 1. And then this becomes 2 times 0 plus 1 times 1. 2 times 0 plus 1 times 1. Okay, so what do we get when we simplify all of these? We're going to get 1 plus 0, that's 1. So we're writing our answer now. It's going to be 1. This is going to be 0 plus 1, that's 1. And this is going to be 0 plus 1, that's 1. Oh, nice. And then we go here. This is going to be 2 plus 0, that's 2. And this is going to be 0 plus 1, that's 1. And this is going to be 0 plus 1, that's 1. And this is the resulting matrix. From this multiplication of A and E, we're going to get a 2 by 3 matrix. It is always important to know what the matrix is going to look like before you even start. So when you make a mistake, you can easily say, okay, I think I'm doing the wrong thing. Number 2, we want to multiply E by A. We're going to go through this again. E is a 2 by 3 matrix. It's a 2 by 3 matrix, and we want to multiply it by A, which is a 2 by 2 matrix. Well, you see that the inside dimensions are not the same, therefore multiplication is impossible. And because multiplication is impossible, we then introduce a characteristic of matrix multiplication, which is the non-commutative property. You cannot switch the matrices and get the same answer. So we can say here that this is impossible. Okay, note, because it's the same two matrices we just played with right now, but we'll have to note that matrix multiplication is not commutative. So matrix multiplication is not. Is not commutative. This is a key thing. Don't lose it. Okay, so to compute BD, all we have to do is say that B is a 2 by 1 matrix, 2 rows, 1 column, and we want to multiply it by D, which is going to be a 1 by 3 matrix, 1 by 3 matrix. Just as you can see, the inner dimensions are the same, so the output of this multiplication will be a 2 by 3 matrix. You read it out here. A 2 by 3 matrix looks like this. 2 rows, 3 columns. So you should expect your answer to look like this. I think just like the previous answer that we had. Okay, so let's do that. If we put it here, it means we have 2, 1 multiplied by, where is D? 2, 0, 1. So remember, we're just going to do the calculation. Now, there's just one column. So you just take the top, multiply it by this. So it's just going to be 2 times 2. What do you get? You get 4. Remember, you already know what your answer is going to look like. It's going to look like this. So it's going to be 2 times 2, you get 4. 2 times 0, you get 0. And you have 2 times 1, you get 2. And you go here, 1 times 2 is going to give you 2. 1 times 0 gives you 0, and 1 times 1 gives you 1. And that's it. You're done. Okay, let's see if it's possible to multiply D, B. So we're starting from D, which is a 1 by 3 matrix, and want to multiply it by a 2 by 1 matrix. 1 by 3 multiplied by a 2 by 1 matrix. The inside dimensions are not the same, so this is impossible. Okay, impossible. Okay, let's go on. The next one. Want to compute 5c squared. Okay, it looks nice. C squared. Now, okay, I'll let you figure that out because there's a question I wanted to ask. This is C. C is a 3 by 3 matrix, so C squared is the same thing as C times C. And as you can see, it's going to be a 3 by 3 matrix times a 3 by 3 matrix. So as long as the matrix is, I don't want to talk about special matrices now, but this is a special matrix because it's a square matrix. This also is a square matrix because the number of rows is equal to the number of columns. So you can easily square them actually. And again, their names are square matrix, square matrix. Okay, so this is the case. You have 3 by 3 because you're guaranteed that the inside dimensions will always be the same, so you can square them. So let's do that. Okay, let's do this. This implies, okay, but now we're going to do all the calculations ourselves. Remember, you take the first row and multiply down, where the first multiplies the first, the second multiplies the second, the third multiplies the third, and you add all of them together, and that's what stays here. So let's go. 0 times 0 is 0, plus 1 times 1 is 1, plus 0 times 0 is 0. So what I have here is 1. Now I'm going to move on to the next row. I want to treat this column first, okay? So I'm going to this column, I'm working on this column now. You're free to go in any direction, but I like doing it this way because now I know I'm taking all these and dealing with just this first column first. So I have, again, just as I did here, I'm going to take this one and behave as if I'm placing it over this. So the first multiplies the first, so that's 1 times 0, you get 0. Then 1 times 1, you get 1. And then you have 0 times 0, you get 0. Oh, that gives you 1 again. I go to the bottom one, I do the same thing. 0 times 0 is 0. Then I have 0 times 1 is 0. Then I have 1 times 0 is 0. So I get 0 here. So I'm done with the first column. So it's as if all the multiplication I did not have this in it. If I did this multiplication, this would have been my final answer. Okay? So I want you to see that. Now let's go. So you have the next one. Want to deal with this column. So we start again from the top. 0 times 1. So that's going to be 0 plus 1 plus 0. That's 1. Mental math now. You have to increase your mental math strength. Okay, we go to the next one. We're dealing with this column. It's going to be 1 plus 1 plus 0. That's 2. Let's go to the next one. Question number 6 is to explain the concept of associativity of matrices. Now, if you do not move them around, you leave them the way they are. A comes before B and B before D. The rule just simply says, it's okay, it doesn't matter which two you multiply first, you will get the same answer. See, that's huge relief. We know they are not commutative, but they are associative, which means that you can multiply the first two, get an answer, and then use it to multiply D, or you can multiply the last two in that order and then use A to multiply it. Okay, basically that. And remember that the primary idea of matrix multiplication is always multiplying from the left. So if you have the choice, every time you're doing multiplication, you want to multiply what is on the right by what is on the left. Okay, so let's just show that this verifies the associative property, okay? Let's see. Firstly, can AB be multiplied? Can we multiply AB? This times this. It looks like we can because this is a 2 by 2 and this is a 2 by 1. So you have a 2 by 2 multiplying a 2 by 1. So what's going to come out of this is going to be a 2 by 1 matrix. And what is D? D better have a 1. Yes. So D is a 1 by 3 matrix. So D is a 1 by 3 matrix, which means that we can multiply. See, we can multiply, and at the end, we're going to get a 2 by 3 matrix at the very end of this. Now, let's see if that is true in this case. We have, again, the fact that we get the matrix does not mean that the matrices will have the same entries, will be exactly the same, but we're going to investigate that. But let's look at BD. Can we multiply? Oh, we got BD. It was number 3. I don't remember what we got, but BD was possible. We were able to get BD. And what was the dimension? Let's see. BD. So this is a 2 by 1 times a 1 by 3. We ended up with a 2 by 3 matrix. So we're going to be having a 2 by 3 matrix on the right. And on the left, what is A? A is a 2 by 2. So because the inside dimensions are the same, we're going to end up with a 2 by 3 matrix. So we know that the multiplication is possible, but does it mean that the entries will give us the same numbers? That's what we want to verify. So let's do it. Firstly, let's do AB. So we're going to have A times B, which is going to be this. 1, 1, 2, 1. We're going to multiply it by B, which is 2, 1. Okay. And then we're going to multiply it by D. What is D? D is, let's make it smaller. D is this way. 2, 0, 1. Okay. We're going to do this multiplication. Or we're going to say it's going to be A, which is 1, 1, 2, 1, multiplied by 2, 1, multiplied by 2, 0, 1. Okay, so we're doing these first. But in this case, we're doing these first. So let's go. If we multiply this, it's going to be, now I'm just going to do what you're supposed to get used to. Use your fingers on your notebook and your paper. Just do this. Place it here, like this. 1 times 2 plus 1 times 1. You see that? This is 1, this is 1. 1 times 2 plus 1 times 1. That's 2 plus 1, which is 3. So I got a matrix. Remember, you have to know the shape of the matrix that's coming out because this is a 2 by 2 and this is a 2 by 1. So you're getting, we're going to get the matrix 2 plus 1. That is 1 times 2 plus 1 times 1 gives us 3. And we have 2 times 2 plus 1 times 1, which is going to be 4 plus 1, which is 5. That's what we get here. And we're going to multiply by 2, 0, 1. Okay, let's finish this. Now let's do this multiplication again. Well, there's only one column, so it's just one multiplication. 3 times 2. So here, remember, we're going to get a 2 by 3 matrix. So the answer to this is going to look like this, 2 rows. 3 times 2 is 6. 3 times 0 is 0, 3 times 1 is 3. We don't need to add because there's no other thing there. And then we go here, we do the same thing. That's going to be 10, 0, and 5. This is the resulting matrix. Now let's see if we get the same thing here, starting from this side. Let me say something generally about number 7. I just wanted to show that AF and FA are not the same. Once you switch, you won't get the same thing. There are special conditions in which AF, that is, the product of two matrices, will be the same even when you switch the positions of the matrices, but those matrices are special. Maybe the 0 matrix, definitely, if a matrix is just filled with a bunch of zeros, whatever you do, whether you put it in front or in the back, you'll always get zeros at the end of it. That's one. Or if it is The identity matrix, it doesn't matter where it is. If you multiply it by anything, it's commutative with any matrix because it doesn't change and doesn't change the result. Or A is the same thing as F. It should be like you're writing C squared, right? Or A is the inverse of F. Now, as we go on, you're going to get to know some of these properties or special matrices. But for now, you should always assume that you cannot switch the positions of matrices unless you know they occupy those special positions in the special matrix kingdom. Never stop learning. Those who stop learning have stopped living. Bye-bye.